us okay, let us continue the second part of today's class. Okay, in the first part, excuse me. Okay, we have told to here. Okay, since it is customary to formulate the eigenbeam forming technique in terms of eigenvalues instead of singular values. Okay, because you can see that eigenbeam forming. Okay, in this word, the prefix is eigen. Okay, so it is related to eigenvalues. Okay, so we prefer to use the eigenvalues instead of singular values. Okay, we note that from matrix theorem section 1.9.2s. Okay, let us go to section 1.9.2s. Okay. Excuse me. Okay. Let A be any complex matrix and denote the singular values of A by sigma I, and the eigenvalues of A times A Hermitian and A Hermitian times A by lambda I. Then sigma I is equal to the square root of lambda I, where I is equal to 1 to the rank of the matrix A times A Hermitian. Okay, let us go back to chapter 3. Okay, sorry, not this. Chapter 3. Okay. An alternative way of expressing D is as D is equal to a diagonal matrix with diagonal elements square root of lambda 1, square root of lambda 2 to the square root of lambda r, where the lambdas denote the eigenvalues of H times H Hermitian. Assume that at some instant the transmitter has R symbols to transmit, which we denote by S tilde, is defined as S tilde 1 to S tilde R transpose. Okay, since the transmitter is assumed to have knowledge of H, it can compute V and perform the following precoding operation. S is equal to V times S tilde. Okay, I think it is naturally for you to ask a question. Why do we need to compute V times S tilde and assign it to S? Okay, we will see the reason later, which results in a transmit vector having the desired dimension nt by 1. Okay, why the dimension of the transmit vector is nt by 1? Okay, let us see. First, the dimension of matrix V is equal to nt by R. Okay, note that the V Hermitian is an R by nt matrix, so matrix V is an nt by R matrix. Okay, and the dimension of vector S tilde is equal to R by 1. So the dimension of S, which is equal to V times S tilde, is equal to nt by 1. Okay. The precoding operation can be thought of as an operation that maps R is smaller than or equal to nt symbols onto nt transmit antennas. Okay, it follows that the received signal vector is given by R is equal to the square root of rho times H times S plus Z, and is equal to the square root of rho times H times V times S tilde plus Z. Okay. Whereas before, rho denotes the total power received at each receive antenna from all the transmit antennas, divided by the thermal noise power at each receiver. Okay, here each receiver means each receive antenna. Okay, so please note that rho is the SNR on a single receive antenna. Okay, since the receiver is assumed to know H, it too can perform a singular value decomposition of H and compute U Hermitian, by which it can pre-multiply the received signal. Okay, I think you may ask a question. Why do we need to compute U Hermitian and pre-multiply it in front of the received signal? Okay. Again, we will see the reason later. Denoting the pre-multiplied received signal by R tilde, it follows that R tilde is defined as U Hermitian times R. Okay. And is equal to the square root of rho times U Hermitian times H times V times S tilde plus U Hermitian times Z. And according to the singular value decomposition, H can be decomposed into three matrices. That is U times D times V Hermitian. Okay. Because U is a unitary matrix, so U Hermitian times U is an identity matrix I, so it disappears. Okay. And again, V is also a unitary matrix, so V Hermitian times V is also equal to I, which is an identity matrix, so it disappears. So finally, we will have the square root of rho times D times S tilde plus U Hermitian times Z. So now you know why we need to times U Hermitian before R, because it will be cancelled with the matrix U. And why do we need to times V in front of S tilde? Okay, because it will be cancelled with the matrix V Hermitian. Okay. So why do we need to simplify the final received signal to this form? What are the advantages of this form? Okay. Let us see the next page. Okay, page 51. Since D is a diagonal matrix, equation 3.22. Okay, let us go to equation 3.22. Okay, in equation 3.22, R tilde, the pre-multiplied received signal, is equal to the square root of rho times D times S tilde plus U Hermitian times Z. So equation 3.22 can be rewritten as the following set of scalar equations. So R tilde I is equal to the square root of rho times lambda I times S tilde I plus Z tilde I, okay, where I is equal to 1 to R. So means that we have R, of these kind of equations. Okay, where z tilde I, okay, here is defined as the ith element of the vector U Hermitian times z. Okay, let us see how to derive this equation. Okay, please see the handout. Okay, please see, okay, page 51. Okay, page 51, problem 1. Okay, I need to change this to the, I need to change the pointer. Okay, good. Okay, page 51, problem 1. How to derive equation 3.23. Solution from equation 3.22. Okay, let us see equation 3.22. Okay, this equation. We know that R tilde is equal to the square root of rho times D times S tilde plus U Hermitian times Z. Let R tilde be equal to R tilde 1, R tilde 2 to R tilde R transpose. From page 45 of the slides, okay, let us see page 45 of the slides. Okay, in page 45, we can see that D is equal to this equation. Okay, so we know that D is equal to DIAG of the square root of lambda 1 and the square root of lambda 2 to the square root of lambda R. Okay, that is, D is a diagonal matrix with diagonal elements equal to these terms. From page 46 of the slides, okay, let us see page 46. Okay, on page 46, in equation 3.19, S tilde is defined as S tilde 1 to S tilde R transpose. Okay, so we know that S tilde is equal to S tilde 1 to S tilde R transpose. Okay, from page 51 of the slides. Okay, let us see page 51 of the slides. Okay, we know this equation. Okay. So we know that Z tilde I is defined as the ith element of U Hermitian times Z for I is equal to 1 to R. Then equation 9, okay, this equation can be rewritten as, okay, first R tilde is equal to this vector, okay, which is equal to R tilde 1 and R tilde 2 to R tilde R. And R tilde is equal to the square root of rho, okay, so it is equal to the square root of rho times D, and D is a diagonal matrix with the diagonal elements, the square root of lambda 1, the square root of lambda 2, and to square root of lambda R. And the off diagonal elements are all equal to 0. And then D times S tilde, okay, S tilde is equal to this vector. So it's equal to S tilde 1, S tilde 2 to S tilde R. Finally, plus U Hermitian Z, okay, and the ith element of U Hermitian Z is defined as Z tilde I. So U Hermitian times Z is equal to this vector. Okay, Z tilde 1, Z tilde 2 to Z tilde R. Then we multiply this matrix with this vector. Okay, and we will get it is equal to an R by 1 vector with elements the square root of lambda 1 times S tilde 1 and the square root of lambda 2 times S tilde 2 to the square root of lambda R times S tilde R. Okay. Then we multiply the square root of rho to this vector. So rho can be moved inside of the square roots, okay, like this. And we plus these two vectors together. Finally, we get this is equal to the square root of rho times lambda 1 times S tilde 1 plus Z tilde 1. And the square root of rho times lambda 2 times S tilde 2 plus Z tilde 2 and so on. Finally, the last element is the square root of rho times lambda R times S tilde R plus Z tilde R. Okay, so we can see that R tilde I is the ith element of this vector, and it should be equal to the ith element of this vector, okay, which is equal to the square root of rho times lambda I times S tilde I plus Z tilde I, okay, for I is equal to R, 1 to R. Okay, so this completes the solution. Okay, let us go back to the slides and turn to next page. Okay, the significance of equation 3.23. Okay, that is the importance of equation 3.23. Okay, this equation is that it shows that by appropriate precoding at the transmitter and pre-multiplying at the receiver, it is possible to decompose a MIMO channel into R SISO channels, each of which consists of a scaled version of the transmitted symbol. Okay, what is the meaning of the scaled version of the transmitted symbol? Okay, it means that it is equal to a scalar times S tilde I, where the scalar is equal to the square root of rho times lambda I plus noise. Okay, noise is Z tilde I. Okay, you may ask a question. The noise should be Z, not the ith element of U Hermitian times Z. Okay. However, it can be proved that if Z is a complex normal random vector, then U Hermitian times Z has the same distribution as that of Z. Okay. So U Hermitian times Z can also be treated as the noise vector. Okay, these SISO channels are sometimes referred to as eigenchannels, and the receiver can decode each of these channels using standard maximum likelihood decoding logic. Okay, I think you have already learned what is the maximum likelihood in the course digital communications. Okay, if you did not take the course digital communications, okay, then you can ask me, okay, by email, using email, and ask me what is the maximum likelihood. Okay, the process of precoding according to equation 3.20. Okay, let us see equation 3.20. Okay, so in equation 3.20, S is equal to V times S tilde. Okay, let us go back to page 52. Okay, sorry, not 52. Okay, 53. And pre-multiplying at the receiver according to equation 3.22. Okay, let us go to equation 3.22. Okay, in equation 3.22, we can see that R tilde is defined as U Hermitian times R. Okay, let us go back to page 53. Okay, it's called eigenbeamforming, okay, which is the topic of this section. Figure 3.2. Okay, let us see figure 3.2. Okay, figure 3.2 shows okay, wait me a moment. A MIMO system using eigenbeamforming. Okay, you can see that originally in the transmitter, the transmitted symbols are S tilde 1, S tilde 2 to S tilde R. And after the precoding V, okay, that is V times this vector, we have the true transmitted vector S1, S2 to SNT. Then we pass the vector S through the channel. And at the receiver, we will receive R1, R2 to RNR. Okay, and this vector, we called it the vector R. Then we multiplied U Hermitian and R together. Finally, we will get another vector R tilde with elements R tilde 1, R tilde 2, R tilde R. So the precoder V and the original channel and the premultiplier U Hermitian together, okay, in this dashed line box are called the effective channel. Okay, figure 3.2 depicts the concept of eigenbeamforming and illustrates the effective channel that is created by the precoding and premultiplying operations. Okay, because equation 3.23. Okay, let us see equation 3.23. Okay, is this equation. Okay, let us go back to page 54. Okay, because equation 3.23 shows that each eigenchannel has a gain equal to the square root of the eigenvalue associated with that channel. Okay, let us back to equation 3.23. Okay, you can see that the channel gain is equal to the square root of lambda I. Okay, where lambda I is the eigenvalues corresponding to the ith eigenchannels, Okay, we see again the adverse effect of small channel eigenvalues. So the channel eigenvalues should be as large as possible. Okay, it is 25 minutes. Let us take a break.